Hi everyone, welcome to this episode of Conjugate Labs. Today we're going to be talking about the concept of conjugate acid-base pairs in Lowry-Bronsted theory of acids. Okay, so we've introduced in the previous video the concept of the Lowry-Bronsted theory and the Lowry-Bronsted acid-base reaction. Okay, but so I'm going to I give you an example that we're then going to kind of feed off. This will help you with some of the examples that you see on the pages of the booklet. Okay, so we're going to look at the reaction of ammonia gas with hydrogen chloride. Okay, I'm not going to write in that they're gas at the moment, but so what we see is that this is one of the cases as to why the Lowry-Bronsted theory kind of makes some sense. Is that these two things are gases, and if you mix them in a tube or in a container and in their gas form, that what you end up with is this solid forming of ammonium chloride, this substance here. Okay, so there's no water involved. You're getting these white crystals kind of forming where the two gases interact within that tube, suggesting that you're getting this different kind of reaction going on. And so what happens is that we can actually think about this in light of what we know about the Lowry-Bronsted theory. We can actually write it like this. So we've got those two gases to form. We can actually consider each ion separately. Now they're part of the solid, so we're going to keep that subscript. I appreciate it looks a little strange, but what we're looking at here is looking at it in terms of two pairs. Okay, so we've got our reactants and our products. And what you can notice is that in this situation that we're getting a proton transfer happening. Okay, and so it's this proton here that's being transferred to attach to the nitrogen, making it NH4, which looks like this. Okay, it's got a coordinate covalent bond. So if I kind of draw it like that, and so the dots represent from the nitrogen, and so that this is where that proton attaches to that lone pair of electrons on the nitrogen. So what we're seeing is that the hydrogen chloride is acting as an acid, ammonia is acting as a base. So the acid is donating its proton to the base, which is accepting the proton to form the two new substances. And so remember, we kind of touched on this in the previous video on the Lowry-Bronsted theory. But so what we can say is that these, and I might clear off this top line too, that we see two pairs happening here. We see or two kind of sets of pairs. The first one, more generally, is looking at that we've got two things on the left, two things on the right, two reactants, two products. But more specifically, we can see that we can link the before and the after for a given substance, before and after the proton transfer has happened. Okay, so if this is before and this is after, we've gained or accepted a proton to go from NH3 to NH4+. These two things are a pair, and we call them a conjugate acid-base pair. Okay, because they're related. So they're related, they're not identical, but they're difference of one proton. Okay, so the acid has one more proton, than its conjugate base. Ooh, you're not going to see that. And the base has one less proton than its conjugate acid for a given pair. Okay, so remember that we're considering this in terms of the pairs. Say like this pair over here, that this base has one less proton than its conjugate acid. This acid has one more proton than its conjugate base, which is the chloride ion over here. Okay, so remember, so we could say that this chloride has one less proton than its conjugate acid. Okay, so you can look at it from both directions here. And so what we would say is that we write these conjugate acid-base pairs using a slash notation. Okay, so we would write the first one like this, and then we could write the second one like this, to show that these are the conjugate pairs that are participating in this reaction. Okay, that and you're seeing it's like the before and after the transfer of a proton. Okay, so kind of keeping that connection so you can see that the transfer of a proton results in a change here. Okay, so I can list off a number of other examples of different conjugate acid-base pairs that we might encounter. Okay, so there's two that we encountered in the previous video, where we were talking about this idea of this hydrogen carbonate ion being amphiprotic. So we have these pairs. We've got so we've got the acetic acid and the acetate ion conjugate pair. We've got water and the hydroxide ion. We've got hydronium and water. All of these conjugate pairs are just some examples that we might come across. Okay, so we can see in each case we've got before and after the transfer of a proton. So showing the connection between these pairs by the transfer of a proton. Okay, so you will often be asked to identify conjugate acid-base pairs, so where you're looking for one thing on one side of the equation linking to something on the other. Okay, so they're not on the same side. So where we had had this equation, NH4 plus Cl minus, okay, these are not a conjugate acid-base pair. These are not a conjugate acid-base pair. Yes, you have an acid and a base, but they are not the conjugates. Okay, because there have more differences between them than they have similarities. Okay, remember conjugates have only a difference of one proton between them. Okay, let's see if I can name that up for you. Okay, so I hope that helps to clear things up a little bit. Thanks very much for watching. Bye for now.